Hello everyone, today we're gonna present our beloved project about cyclic behavior of unborn post-tension precast concrete beam column connection with bucking restrained knee brace. In the past, most of the construction used cast-in-place concrete, which had a problem in quality, time, and used a lot of formwork inside. Then precast concrete can be solved the problem of cast-in-place in terms of great quality and fasten in construction. However, precast concrete is not suitable of earthquake due to the weak joint. According to 1994 Northridge earthquake, most of precast concrete structure collapsed. Therefore, precast structure would not allow unless the performance is proved and verified. After that, the researchers study and improve about the joint of precast system, which can be divided into main systems. First is monolithic, which attempt to emulate cast-in-place structure by casting concrete at the joint, which can dissipate energy well but cause crack or failure in the connection. To avoid damage of beam column connection, jointed precast is developed, which can limit damage to the contact area of the prefabricated part. Therefore, hybrid frame will be used in this study that have pre-stayed tendon to help self-centering, moment resistance, and shear resistance that combine with mass steel reinforcement, which help energy dissipation. However, after the earthquake occurred, the reinforcement was damaged and hard to repair. Therefore, to replace and repair easily, our study will convert the energy dissipator by changing internal reinforcement into the external bracing, which using buckling restraint brace or BRB to dissipate energy, which the steel core can prevent bucking. Moreover, unborn material that wrap around the steel core can prevent tensile and compressive force. And this study had the objective to study the seismic behavior of post-tension precast concrete joint improved with bucking restraint knee brace or BRB. And second, to compare the failure mode, strength, stiffness, and energy dissipation of having BRB and without BRB improvement. And lastly, to highlight the advantage and disadvantage of post-tension precast concrete joint improved with BRB. And our study bases on the design of 5-story building in hybrid structure and scaled down in 2 to 3 from the actual structure. Next is the design concept that design hysteretic behavior of post-tension tendon to self-centering well as shown in bilinear elastic graph, while design of BRB to dissipate energy as shown flat loops, and the combination of post-tension and BRB show flag-shaped hysteretic loops that perform best seismic performance. And design the structure by using capacity design. First is the fractural strength at the hybrid connection must be large enough to withstand the lateral forces from the earthquake. Second is the rotational resistance capability of the hybrid connection must be sufficient. And lastly, the structure must have a lateral deformation based on a strong column weak beam mechanism. After that, preset tendon should be designed on elastic zone for self-centering and even have no lateral load. Preset tendon will be designed to capable of shear force and factor load. And our study will place preset tendon in the top and the bottom to increase moment arm, which can increase fractural strength of the structure, while designing BRB at U point that in elastic zone to dissipate the energy. Lastly, the moment will be shared and transferred to BRB and pre-state tendon. Then using moment of BRB divided by total moment of BRB and pre-state tendon must equal or lower than 0.5 to ensure self-centering and energy dissipation, which the suitable value should be equal to 0.3.
For methodology, we make specimens from cutting the external joint section of real structure that we observe and scale down to thirds. There are 3 important parts, including the beam, column, and bracing BRB. For the first setup design, we designed them cross-set to the real structure that we observed, but later it had been modified by placing the column in the horizontal plane and placing beam in vertical plane to make it easier for experiments and save budget. The column force will equal the beam force multiplied by factor the 0.562. For our experiment, we will compare between 2 specimens. There are the first specimen on the left-hand side, named UPPC, stand for unborn post-tension precast concrete, and the second specimen on the right-hand side, named UPPCB. There is the same detail as the UPPC, but at more bracing BRB, and the tendons are put with a force of 0.5% of strain, and the BRB moment over total moment will equal 0.4. After completing the experimental design, the sample were installed in the preparation for the test and setting by pivotal load by hydraulic jack at the end of the column and had a steel frame to prevent the torsion on the beam. And start testing by apply load at various story depth. Start from 0.25% both forward and backward for 3 cycles and gradually increase to 3.5% for 3 cycles, the same as every story depth and every specimen. For the result of this experiment, first consider the heuristic graph of both specimens. UPPC will show the advantage of self-centering when receives the cyclic load, and UPPC basing will show the advantage of good energy dissipation more than the another specimen. Next is the envelope graph. Will show the maximum force of two specimens and compare them. You will see at the same story depth UPPC basing can get more than 4 and UPPC basing graph had a slope greater than the UPPC specimens, represent a greater stiffness.
For the criteria used to ensure the performance of the frame, specimen UPVC was used as acceptance criteria for moment frames ACI 374.1, which use the parameters as shown in the slide. When calculate the limit on real drift ratio, the value is 3.6%, so 3.5% was selected to compare to the acceptance criteria. For specimen UPVCB, the design of BRB is not yet governed by any building code, so Lopez that designed test the frame with BRB based on the recommended provision published in FEMA 45 knot was used as a reference in this study, which used the design story depth of 2%. When calculate the limit on real drift ratio using the R value between 6 and 8, referring to Mayaport standard for steel building frame system, the value is in the range of 2.18% to 2.9%. So 2.75% drift is the reasonable value to compare to the acceptance criteria. This line graph shows the stiffness degradation for both specimens. The normalized secant stiffness is used to compare to the acceptance criteria. The normalized secant stiffness shall not less than 5%. For the specimen UPVC or the specimen without BRB, the normalized secant stiffness at the 3.5% story depth was 25.6%, while the specimen UPVCB was 18.8% at 2.75% drift. It means that both specimens perform an acceptable stiffness degradation. Although the specimen UPVC perform a better ability to withstand the degradation of stiffness than the specimen UPVCB, the energy dissipation also needs to be confirmed in order to ensure the performance of seismic resistance. For the energy dissipation, in order to check whether the behavior of energy dissipation for both specimens will pass the acceptance criteria or not, the relative energy dissipation ratio then therefore calculated and plotted. The relative energy dissipation ratio has to perform above 12.5% according to the acceptance criteria, but the specimen UPVC was only 2.25%, while specimen UPVCB performed 21.6%. It is clearly shown that the energy dissipation behavior of specimen UPVC was not satisfied the acceptance criteria, while specimen UPVCB was satisfied. Next is to ensure that the experimental results are following the assumption or not. The first assumption says that the connection deforms at rigid bodies or deform only at the beam column interface. Second is the inelastic behavior occurs only at BRB core, which means that the precast beam and column including post-tension tendons should remain elastic behavior shown in the number 3 and 4. In this study, 3 major types of deformation were measured for both specimens consisted of fractural, shear, and rocking deformation. In comparison of both specimens, it was found that the fractural beam rotation and the joint shear deformation did not play a significant role when compared to the rocking angle deformation shown in the gray area. The important deformation was observed at the beam column interface, which deformed like a rigid body as expected. Next is the strain of post-tension tendon. It can be seen that the maximum observed strain for both specimens are lower than the allowable strain, which means that the post-tension tendon still remain elastic behavior after the completion of the test. The last one is the strain of reinforcing steel. Both specimens were contributed by 3 sizes of steel, which are DB16, RB9, and RB6. From the results, it can be seen that the strain of reinforcing steel for all 3 sizes was significantly lower than the yield strain, which means that the reinforcing steels can totally remain elastic behavior as expected. It can be concluded the post-tension precast concrete connection with BRB can perform higher strength, stiffness, and energy dissipation than the frame without BRB. This alternative frame system can also limit the damage only at the beam column interface, and no damage observed at precast beam column, which is easier to repair after subjected to seismic load. Thank you.